Hello everyone, my name is Amin Babadi. I'm a PhD candidate in computer science at Aalto University, Finland, and here I want to present our paper that I have worked on with Perto Hämäläinen, Shashama, and Jaakko Lehtinen from Aalto University and NVIDIA. In this paper, at first, we studied Proximal Policy Optimization, or PPO, which is one of the most popular and powerful reinforcement learning algorithms. And we then found out that there is actually a caveat to this algorithm, and it's that PPO can prematurely converge, which leads to slow progress. We then, in order to mitigate this issue, drew some inspirations from CMA-ES to propose our own algorithm called PPO-CMA, which is a proximal policy optimization algorithm that can adaptively expand the exploration variance to speed up progress. We have tested our algorithm and compared it with the original PPO and found out that PPO-CMA can significantly outperform PPO in continuous control benchmarks and that it is also less sensitive to the choice of hyperparameters. Just to clarify, I must say that we are interested in continuous control problems. You can see two examples here where the goal is to optimize the torque values for the character joints such that when we simulate the physics, the characters walk forward. On this slide, you can see a diagram of a typical reinforcement learning system. Such a system usually includes an agent and an environment interacting with each other. So at each time step of the interaction, at first the agent observes the current state as t, and then it uses its internal policy, which in our case is a neural network, to map that state to its next action at, and then it executes that action, and the environment then responds with a scalar reward rt plus 1. This loop goes on, and the goal is for the agent to optimize its policy such that the accumulated reward over time is maximized. One of the most popular family of reinforcement learning methods is called policy gradient, and its idea is simply to update the policy parameters by estimating the gradient of some loss function. And there are some options for the loss function in policy gradient, and I'm showing one of them that we are interested in here. So this one is assuming that we have m data points that we have simulated using our policy, and then it uses a function called advantage function, or API, that measures the benefit of taking action AI in a state Si. This function is usually either positive or negative depending on how good the action was. And our policy pi theta models the probability distribution of action given current state. And to model this function, is common to use a neural network Gaussian policy, which outputs a state-dependent mu theta and covariance matrix c theta. And if we do that, we can actually rewrite this loss function like this. And if we try to minimize this loss function, we are actually increasing the probability of taking actions with higher rewards. One of the most famous policy gradient algorithms is called Proximal Policy Optimization, or PPO. It has been published in 2017. There are actually two main ideas behind this algorithm. The first one is that at each iteration of PPO, it performs multiple mini-batch steps to the same data. And the second one is that it ensures stability by limiting the divergence between the old and the updated policies. It has actually shown remarkable results since it has been published, and you can see 3 examples using PPO here. But as I said, there is a caveat to PPO algorithm that I will try to explain here. So the first one is instability of multiple mini-batch updates, and it's that when we perform multiple mini-batch gradient updates without updating the advantage values, we realized that policy gradient can become unstable because of the negative advantage actions. So this is shown in here. In the figure, we can see the negative advantage actions in red and the positive advantage actions in green. And the sampling distribution of the policy is the bold black circle. And as you can see, after applying 100 mini-batch updates, the policy is actually jumping over the optimal solution. PPO prevents this kind of divergence from happening, but it comes at the cost of prematurely shrinking the exploration variance, which is shown in the second row of the figure. Our PPO-CMA algorithm, however, manages to fix this problem and successfully expanding the variance towards the optimal solution. Another issue with PPO is its premature convergence, which is shown in this problem. As you can see, it's actually converging before reaching the optimal solution. Our PPO-CMA algorithm, however, manages to solve this problem really quickly by finding the optimal solution. But before explaining how we designed PPO-CMA, I need to give you a short recap of CMA-ES, which is a black box optimization algorithm. And the way CMA-ES works is that at each iteration, it draws some samples from the sampling distributions, and then it evaluates them using some fitness function, and then it uses the fitness values to compute the weights of the samples. Finally, it updates the sampling distribution mean and covariance using those weights. An example of CMA-ES solving an optimization problem is shown here. As you can see, CMA-ES manages to quickly expand the exploration variance towards the optimal solution and solving the problem really fast. So this is a property that we were really interested in, and we wanted to see how we can simulate this behavior in the context of PPO. In order to do that, at first we wanted to answer this question: how does CMA-ES avoid premature convergence? We came up with three reasons in this algorithm. The first one is that when CMA-ES wants to update its sampling distribution, it only uses the positive weight samples. This is shown in figure A and B here. In figure A, you can see that the sample data points in blue, and on the right, you can see that CMA-ES, after evaluating the samples using the fitness function, is ignoring the worst 50% of the data. The second reason is called rank mu update, which means that CMA-ES at first updates the covariance and only then updates the mean of the sampling distribution. And the third reason is called evolution path heuristic, which means that CMA-ES uses an additive term to further elongate the covariance along the most promising direction to increase the exploration in that direction. And this is also shown in figure C. You can see CMA-ES is expanding the variance towards the optimal solution. Okay, now I can explain how we designed the PPO-CMA. At first, we chose to use a standard policy gradient loss function, which I explained earlier. And then, since we are not using the PPO's loss function anymore, in order to ensure stability, we train only on actions with positive advantage estimates, which is similar to the CMA-ES algorithm. By the way, we also came up with the idea to also include the negative advantage actions into the optimization process, but I will explain that in the next slide. The second idea was to use separate neural networks for policy mean and variance to be able to implement the rank mu update of CMA-ES, meaning to be able to update the variance before the policy mean. Finally, to approximate the evolution path heuristic of CMA-ES, we use a history of training data over multiple past iterations to be able to find a direction between iterations if there is one. As I said, we realized that it might not be the best idea to completely disregard the negative advantage actions because they can potentially have some valuable information in them. So in order to also use them, we came up with a simple mirroring technique shown here that can convert the negative advantage action AI to a positive advantage one A prime I. This is also shown here in the figure. As you can see, the red The red dots are the negative advantage actions, and the green non-full circles are the converted versions of them using this formula on the left. So this is the pseudocode of our PPO-CMA algorithm. At each iteration, we at first sample n data points using the policy. Then we train the critic network using those experiences, and then estimate the advantage values. So up until this point, everything is exactly as in PPO algorithm. But after that, we either remove the negative advantage actions or we convert them into positive ones using the technique that I explained in the previous slide. Then we train the policy variance network using experiences from the past H iterations. And finally, we train the policy mean network using the experience from the current iteration. As you can see, PPO-CMA is fairly simple to implement, and one can use the available deep learning libraries, for example, TensorFlow, to implement the loss function and the neural network. To be able to fairly compare PPO and PPO-CMA, at first we did a hyperparameter search for both algorithms. You can see on the left the search for PPO hyperparameters, and on the right you can see the same for PPO-CMA. The scores here are normalized between 0 and 1, with 1 being the highest found score. And better scores are also shown with darker colors. As you can see, PPO-CMA is actually doing a lot better than PPO, and also is less sensitive to the choice of hyperparameters. And you can see the more detailed results over 9 different RoboSchool environments here, where PPO-CMA is shown in green and PPO is shown in red. As you can see, PPO-CMA is doing a lot better than PPO, and it's only showing comparable results in only a few environments. On the right, we chose to compare these algorithms on a more complex environment. So on the right, we compared them in the more complex 3D humanoid of Mujoko simulator. In this environment, it's common to use higher sampling budget per iteration. So we use different versions of both algorithms. Here, red and blue are PPO-CMA, and the rest are PPO. As you can see, PPO-CMA is doing pretty well in this environment, as opposed to PPO, which is not learning anything useful. To summarize, in this paper, we studied Proximal Policy Optimization, or PPO, which is one of the most popular reinforcement learning algorithms. We then showed that one of the caveats of this algorithm is that it can prematurely shrink the exploration variance, which leads to slow progress. We then adopted some ideas of the famous CMA-ES algorithm to episodic RL to propose our PPO-CMA algorithm to mitigate that issue. And we showed that PPO-CMA outperforms PPO and does not need tedious hyperparameter tuning. Finally, you can see the link and the QR code to our GitHub repository here, where you can find the source code of our PPO-CMA implementation. For more details, you can refer to the paper, and in the archive version, which you can find in the GitHub repository as well, we have included some additional results. And by the way, the first author of the paper, Professor Perto Hämäläinen, who is also my PhD supervisor, didn't have time to present this paper, but you can reach him using his email if you are interested. Finally, I wanted to thank you for your attention, and I will be happy to answer any questions that you might have. Thank you very much.